Hi, Mitch Wenger back with another video on data analytics and machine learning. In this video, we'll discuss ranking. Hope you enjoy. Okay, let's get started. We've spent a good bit of time and effort figuring out how to calculate EV. Yet EV, like accuracy, boils a fairly complex process down to a single number. It's good to keep in mind that many stakeholders prefer a simple, easy to digest view of performance. Others, however, even seasoned data science professionals who understand the details behind EV, may find a single numeric measure too simplistic. For the most part, they understand that a single value places great reliance on the spot-on accuracy of all the assumptions and estimates. Do we really know exactly how the population will behave? Do we truly know the exact costs and benefits for our various outcomes? Instead, it's useful to present model performance across a spectrum of possible values for our assumptions. Sure, we can present such ranges numerically, but humans typically interpret such data better visually. The first assumption we can address is the notion of classification. In our typical tree-based or regression-based classification models, we classify each instance individually, then take the appropriate action for that instance. Now, another way to make decisions is to create a ranking of all our cases, and then just take action on the topmost cases. Now, this approach can be useful for a variety of reasons. First, some models don't actually create a class prediction or even a class probability prediction, but simply a score for each case that can't truly be converted to a probability. It could be that we can't really get a good class probability estimate for a variety of reasons. Maybe our training sample doesn't represent the population as well as we'd like. Even if this is the case, the score our classifier creates may still be useful, especially when we compare it to the scores for other cases in our dataset. Next, we may have a budget that only allows us to take action for a certain number of cases. In such a situation, we want to make sure we target our efforts toward the highest likelihood cases. Of course, we want to be careful that the budgeted number of cases isn't so high that we begin to include negative expected value cases. Finally, costs and benefits may be somewhat fuzzy, so we can't really prepare a precise estimate. Regardless, we want to pursue the highest likelihood cases with the expectation that those will provide some positive return. Of course, if we start considering that individual cases may have different benefits and even costs, that complicates things. A simple ranking in this case may not suffice. But if we're still considering average costs and benefits across a broad population, it's a nice approach. Let's consider how to create a classification when all we have is essentially a score for our example. We may want our classifier to be very conservative, in which case we only assign the positive class if we have a relatively high level of certainty. In this case, we would assign what we call a high threshold to the classifier. In other cases, we can be more permissive in assigning the positive class, in which case we can lower the threshold. So, what do we mean by threshold? Let's take a look. Let's say we have 200 instances in our dataset and our model assigns a score between 0 to 500 for each case. The way our model is set up, higher scores are more likely to belong to the positive class. So, how do we go about predicting which instances are positive? Let's take a look at different thresholds. If we set our threshold at 480, we will only predict instances with scores of 480 and above to be positive. From there, we can create a confusion matrix for our model, like so. And as you can see, we don't have any instances in that predicted yes row. So next, let's lower our threshold to 475. Here you can see that we predict one positive instance and end up with a different confusion matrix. And we can continue this process each time creating a new confusion matrix based on our threshold. Next, we can see what happens when we set our threshold to 470. 460. And finally, 440. Each time we lower the threshold, more of the instances move into the Y row of the confusion matrix. So as you can see, we have now decomposed our model evaluation one more level. And as it turns out, this ends up being useful in those situations we've discussed earlier in the video. We can't necessarily assume that our model gives us a precise probability for class membership. Even if the model does give us a probability, we can still treat it as a score instead and rank our instances. We can then set an appropriate threshold for our business problem. We'll discuss this more in upcoming videos. That's it for this discussion on ranking classifiers. I hope you found it useful. As always, be sure to check out the other videos in this series.